Hello, everyone. Today, I thought it would be super hip to talk about TimeScaleDB. This is a Postgres extension that is geared towards time series data. I'll talk about what TimeScale is, what materialized views are, and the many cool features my team and I have gained with TimeScale Managed Service. I'm going to preface this with I'm by no means an expert. These slides are based on my learnings and timescale documentation. Fortunately, timescale is very well documented, and I invite you all to check those docs out. With that, let's get this party started. So about me, hi, my name is Michelle Yuen. I am a software developer for the Adler Planetarium in Chicago. You're probably thinking, that sounds pretty awesome. And you are absolutely right. It is out of this world, pun intended. More specifically, within the Adler, I work with maintaining our citizen science platform, Zooniverse.org. Now that introductions are out of the way, let's get down to business. To start off, what is TimeScale? Per the docs, it's a high-performance Postgres extended for time series data and analytics. So what does that mean? Basically, it's a database designed to harness the full power of SQL, as well as our existing knowledge of SQL, in order to deal with problems that people tend to have when dealing with time series data stores. Some issues, for example, are like dealing with large data volumes and querying that large data store for analytics. So what exactly is time series data, and how does it differ from regular data? When we talk about time series data, we're talking about metrics or event monitoring. Said another way, time series data is data which represents how a system, process, or even behavior changes over time. For example, weather conditions measured every hour, or even your battery life on your smartphone. I currently have 78% battery. Those are some examples of time series data. But what makes it different from regular data? Biggest difference is that time series data, with time series data, time is our primary axis. So now we have a general idea of what timescale is. Let's talk about what we get with timescale. For time's sake, I'll mostly focus on the features that I've used at this point in time. One key feature is the hypertable. Hypertables are Postgres tables with special features that make it easy to handle time series data. Technically speaking, a hypertable is a table partitioned by time consisting of smaller chunk tables. TimeScale does this so that whenever you query over the hypertable, Postgres farms out the query to the smaller chunk tables, very much like a MapReduce solution. So you can think of a hypertable as one big table full of tables of all the same structure. These mini tables we call chunk tables that are chunked by time in our case. To really reinforce the idea of what a hypertable is, we'll look at a very abbreviated example. Imagine we have a table where the columns are time and value. In a normal table setting, it'll look just like normal rows and normal columns, all in one table. In a hypertable setting, our hypertable consists of chunked normal tables, all with the same columns, time and value in our case, chunked by day or whatever time interval we choose. So in this example, we can see 3 events on January 2nd, 2021, one at midnight, one at 0600, and one at 2300. In a hypertable setting, these 3 rows live in this chunked table, chunked by day, January 2nd, 2021. Same thing with the events on January 3rd, 2021, And then same thing for the events on January 4th, 2021. What's nice is that TimeScale automatically chunks our hypertable into time buckets, so we don't have to think about it. This is all taken care of in Magic that we don't really have to touch, all living under the hood of the extension. Another nice thing is that when querying from hypertables, our query syntax will look the same as if we're querying from a normal table. Because in the end, under all this beauty, it's just Postgres. Feel free to quote me on that. And that's the awesomeness of it. To get a bit technical on why hypertables aid us in speeding up query execution time, when we send an incoming SQL query, the Postgres planner analyzes the query and routes it to the proper chunk table based upon our query's conditions. So cool. We get hypertables that speed up our queries and help manage our data. In an environment of hundreds of millions of data entries where users expect our query response times to be fast, dare I say hyper fast, this feels necessary. So what else do we get with TimeScale? We get to utilize continuous aggregates. These are background workers built into the database that can group data by a schedule. Just to give some perspective around this, time series data usually grows very quickly. And that means that aggregating data into useful summaries can become very slow. Reason being, every time we run these aggregation queries, the database needs to scan the entire table and recalculate every time. With continuous aggregates, aggregating data becomes lightning fast, and it does this by utilizing and improving upon Postgres Materialized Views. How does it improve Materialized Views, you may ask? Very good question. But first, I think it's best to explain what Materialized Views are, since that is what continuous aggregates are based on. Then we'll go into an in-depth explanation and example on continuous aggregates and its improvements. So materialized views are snapshots of a query that stores the results in a special Postgres table that we can view from / read from later on. As an example, pretend we have an application with an accounts to orders table. Hopefully you can read this. Okay. Imagine we have an application with an accounts to orders table. So here we have account A with order 1, account B with order 2. We have an inventory table with items in stock, in this case, shirts and pants, with their item IDs and how much we have in stock. And we have an orders table that tells us how much of each item was ordered. Say we wanted to know the total of each item that was sold. We'd have to roll up the quantity of shirts that were sold. So in this case, shirts have item ID 30. Order 1 has a quantity of 2 shirts in their order, and order 2 has a quantity of 2 shirts in their order for a total of 4 shirts. And we'll do the same thing for pants. In this case, we only have 1 order of pants with a quantity of 3 to make a total of 3 pants sold. Oops. Oh no, come back. Okay, my bad. Instead of having to run this query every time, we can read our materialized view, which saves us from doing this complex query again. So how are continuous aggregates better? One thing about vanilla Postgres Materialized Views is that they don't update regularly. We'd have to manually refresh them as required. With continuous aggregates, we get the functionality of Materialized Views, but we also get the ability to automatically refresh those views without us having to do a refresh manually and without losing any historic aggregated data. Okay. So hopefully we have a general sense of what materialized views are. We're going to go in depth and view how continuous aggregates utilizes materialized data to speed up queries. When we create a continuous aggregate, TimeScale takes the raw data from an underlying hypertable and aggregates it over a set time interval, and then materializes that aggregation. As an example of what we might want to aggregate, say we have a table full of events and want to count how many events came in each day, or even each month, or even each quarter, etc. Instead of querying the whole table to grab this count, we could run a query every 24 hours to aggregate the previous day's event counts and store that pre-computed value somewhere or in some sort of view for us to grab easily and quickly whenever we need it. And that's essentially what continuous aggregates are. They're optimizations of queries by pre-computing the results and allowing us to utilize the aggregated results to serve for our queries. Okay, let's see this in play. I actually ran a proof of concept using a replica of Xuniverse's database, where I created a hypertable full of what we call classifications. You can think of them as events or occurrences, just data entries, and a continuous aggregate that aggregates the classification classification count per specific workflow per day from the hypertable that I created to do some comparisons. To give you some perspective, within the Xuniverse, we have a little bit more than 750 million classifications and counting. That's a pretty big table. I'll bring this back. If we wanted a count of classifications in this particular workflow with ID 4403, when we do this in a normal table setting, after 1,000 runs, we get an average execution time of about 3.6 seconds, which is 3,600 milliseconds. If we grab the count of classifications in a hypertable setting, where these classification events are chunked by day in a hypertable setting, this is what our query would look like. Select count star from classifications where workflow ID equals 4403. Note that this query looks like the same query as if we were querying from the normal table, but in this case, our classifications table is actually a hypertable. When we do this query, we better our execution time with an average of 293 milliseconds. If we create a continuous aggregate of our classifications hypertable that aggregates classification count per workflow per day, and then sum those classification counts to get us the same results of these queries, we better our execution time to 43 milliseconds on average, which feels like a really great optimization. All this amazing stuff are some of the features of TimeScaleDB. Okay. Now that we got to see what we gain with TimeScale, let's go over a small example of how to implement this into into new Rails apps. Okay. I'll show you what the final result of what we'll be building with our example. In our case, our users are interested in how many classifications are done in our project each day, or each week, month, year, which they can pick what time bucket they want to choose through this drop down. Our default view will be bucketed by day. First, after we get our Rails app set up, and we will enable TimeScale onto our apps like so, enable the extension TimeScaleDB. Then we are going to create a hypertable in a migration. We create our table first, classification events, which have the columns classification ID, event time, which is the time the classification was created. You can think of it as a created at. and the user ID, which is the ID of the user who created the classification. We utilize a composite primary key because if we recall, with TimeScale, time is our primary axis for time series data. So we want to index by time. And for our particular case, we also want to keep indexing by classification ID as well. Once our table is created, we're going to turn our classification events table into a hypertable with our time axis being the event time column. We do this by utilizing the create hypertable function, which is a TimeScale function. It takes in the table name and what column is our primary time axis. Okay, this one's a big one, but we'll go through this one piece by piece. Okay. We're going to create our continuous aggregate. In this case, we'll execute a SQL query to create a materialized view called daily classification count, bucketing each event time by day, and saving each entry as a total count of classifications for that day. We also want to create a refresh policy that triggers that continuous aggregate to refresh the materialized view and do any recalculation given a specified time period look back and on a scheduled interval. Here, our refresh policy runs every hour with the scheduled interval, and then looks back at the past day, at data from the past day up to the current hour to create or update a record within our materialized view. We'll create a model for our materialized view / continuous aggregate. We called it daily classification count in our case, to make it easier for us to interact with and query from. It's a read-only table since it's a materialized view. Then in our controller, when we query bucketing by a specific time period, in our case, day, week, month, or year, we'll run a select query on our continuous aggregate view, bucketing by a specific time period, and then summing the daily counts if needed. Yeah, that's pretty much all I had. Thank you so much for listening to me. Here are my social medias. Let me know if you have any questions, and thank you all so much.